This live SLU show is brought to you by the support of SLU members and the following sponsors. Visit SLU.com to become a member today.
Hello and welcome to this live SLU show on SLU.com. My name is Will Gator, and tonight, well, this morning, we're celebrating the perihelion of Rosetta's comet, Comet 67P Churyumov-Gerasimenko. Now, Churyumov-Gerasimenko is currently some 266 million kilometers away from the Earth, and over the next couple of days, up until the 13th of August, it's going to be getting really close to the sun. And so we're celebrating that moment, a moment when really something that Rosetta scientists have been looking forward to for a long, long time. Now, we've got some fantastic guests coming up on the show. We're going to be speaking later on in the show to Rosetta's project scientist, Dr. Matt Taylor, and we're going to be talking about some of the secrets that really the probe has allowed us to unlock and learn about this comet and comets in general. Of course, one of the things we always do here on SLU is try to bring you live images of the night sky. And we're going to be doing something very special tonight because, as well as talking about the science of the comet, we're also going to be bringing you live pictures of 67P. So hopefully in the coming minutes, we'll be able to show you those pictures. We've had a little bit of trouble with cloud bubbling up over the mountain tonight, Mount Teide, where our telescopes are located in the Canary Islands. But hopefully we'll be able to bring you those live pictures. But we're also going to be doing something even more special. We're not just going to be looking at the comet with our own telescopes. We have enlisted the help with one of our partners, the European Space Agency, of the optical ground station on Mount Teide, on the observatory there in Teide. And that is a 1 meter aperture telescope, and hopefully we'll get live pictures of them, live pictures from them this evening. I think we can actually see a live view of the control room at the optical ground station, actually get a view inside. We're basically waiting for those images to come down from. Now, I think we can go to a live view and see the sort of live all-sky view of the sky of what we're dealing with in the Canary Islands. That's the view at the moment. You can see SLU's telescopes, the domes there, and that bright object is the moon. So hopefully that cloud, which is just in the way of where we want to see the comet, hopefully that will move out of the way in the coming minutes. We've got until about past. We're racing against the twilight because, of course, the reason why we're doing this show at this particular time is because this is when the comet is visible from our telescopes in the Canary Islands. And to talk about our scopes and what we plan to do this evening, I'd like to bring in a good friend of the show. It's the SLU Observatory Manager, Paul Cox. So, Paul, I wonder if you could tell us a little bit about the sort of problems and issues we've been dealing with this evening and the sort of things that we can hope to see if that cloud clears.
Hi, Will. Well, yes, as we can see there, we've got this low cloud that actually enveloped the entire observatory site. And remember, we're 8,000 feet up. That's a couple of thousand meters altitude at the top of the volcano at Mount Teide. And the whole thing was enveloped by this cloud. We had to close the observatories. The European Space Agency guys had to close their dome. But would you believe, 20 minutes before the show began, the cloud is just going down. But just above there, on this all-sky camera, Will, we can see the moon shining brightly there, illuminating those clouds, those pesky clouds. And just to the left of the image, that is the SLU half-meter telescope. This is the telescope that SLU members control every night. And you can see it pointing to where Comet 67P is right now. And we are getting a few images coming through these clouds. So we've got some great things to look forward to.
Fantastic. That's really good to hear because, of course, that's what we want to see. We want to see those pictures because actually the comet's near a lovely cluster this evening, isn't it?
It is. It's actually close to two star clusters. They're open clusters of stars. They're really quite old. I think one of them's called Messier 35, and the other one is a smaller star cluster, but it looks more like a globular cluster. So in our images, we're going to see a large cluster of stars, kind of the top left of the images, a small cluster of stars down at the bottom right, but then just to the bottom left, we're going to see the little smudge, which is 67P, which is absolutely amazing when we kind of make that connection and think while we're watching this tiny little comet as it's nearing its close encounter with the sun, that the Rosetta spacecraft is orbiting it right now when we see those images. So that's what's exciting for me, Will.
It's fantastic, isn't it? And another thing that we should say is that it's not just our telescopes that we're working with this evening. We've partnered with the European Space Agency to use their optical ground station telescope, and that's quite an interesting observatory, isn't it?
Oh, it's fascinating. It's one of the largest at the Mount Teide Observatory, and they do all sorts of strange things. Quite often, SLU members in this all-sky view will see a green laser shooting up through the sky, and that's from the optical ground station. We'll maybe talk about that when we interview the guys who are controlling the optical ground station, the ESA guys who are controlling that tonight. But they also monitor near-Earth asteroids with that telescope, and also space junk, Will. And that's been in the news very recently because the International Space Station, they all had to climb into the emergency craft, didn't they? Because they thought an old bit of space junk was maybe on its way to the space station. But there we are live. I'm actually going to be talking while you're interviewing our fantastic guests. I'm going to be talking direct to the guys in the control room because we're still waiting for them to be able to get their images up and online for us.
It's an exciting moment as we wait for those pictures, and as you said, we've got lots more coming up in the show. And if you're following along with us on social media using Twitter, and if you're up this morning, say hello. And if you've got questions, maybe you've got questions for some of our guests, maybe for Paul or maybe Dr. Matt Taylor, who we're going to be speaking to very shortly, then you can use the hashtag #SLURosetta to ask questions. But yeah, it's very exciting because I've just seen in the corner of my eye, our producers just said that we have the first live pictures from our high magnification
Woo!
telescope on the Canary Islands. So there we are. And actually the
Excellent.
comet, isn't that fantastic? So there is that beautiful star cluster M35, and there is NGC 2158, which is that little cluster down in the bottom right hand corner, isn't it?
That's right. And they are looking glorious. This image will turn into color. So that's M35 that was being pointed to. And that's the little star cluster down at the bottom right, NGC 2158, as you said. And the comet is a little smudge over to the left. Hopefully our producer will be able to point to that. In fact, we've got a diagram which will help viewers to actually spot exactly where it is. But Will, it's actually quite faint, isn't it, this
It
comet?
is. It is, yeah, and actually, we were looking at the chart earlier on. If you look at those two stars that are sort of just below center in our live picture, and then sort of track along to the left a little bit, there's a very, very faint smudge in that picture, and that is the comet. And this is what I think is so incredible about what we're doing tonight, because although that might seem a little bit underwhelming, it's what you said earlier. That there is the comet that Rosetta is at. We sent a mission there,
I
well,
know.
not we. We'll speak to Matt Taylor later. He sent a mission. He and
Yeah.
his colleagues sent their mission. They're orbiting around it, and we've got these incredible views. We can see this strange object with its cliffs, its jagged outcrops, and more recently these incredible jets. So I think this is what's lovely is even though it's a tiny, tiny little dot in this image, a fuzzy ball, it brings that to life, doesn't it? It really brings this to life to know what we're looking at.
It does, and we're going to see the great thing about this particular comet. We're going to talk about it when I come back on the show at the end. We're going to be talking about what SLU members have been doing, Will, and we're going to be looking at some of the images that they've been taking actually for the last several months. And in fact, we've even got images from way back in the early 2000s that members have been taking of this periodic comet. So we've got some great things to look forward to, as well as these beautiful. I mean, how fortuitous it is that our show tonight, I wish we could say this was planning, but the Comet 67P just happened to be passing M35 and this other star cluster tonight. And we only found that out a couple of days ago. So that was fortuitous.
Yeah, it's fantastic. And we've got lots coming up here over the coming weeks on SLU. Give you a little preview of what we've got coming up, even just in the next few days, in the next week. We've got a live Perseid show on Wednesday, the 12th of August. That's at 1 a.m. Eastern time. Sorry, that's the 67P show, where we're basically looking at the comet at perihelion. The same day, because we've got so much on, the Perseid show is the same day. So we're doing a live broadcast of the Perseid meteor show. That's that fantastic summer meteor shower. It's a great opportunity to get out there with your friends and look at the night sky and see if you can see some of these beautiful meteors. And I know, Paul, I'm going to be talking to you later about some very cool things that we've got planned for that particular show. So perihelion's coming up in just a few days on the 13th of August, and we're going to have that live show on Wednesday. But for the moment, we're going to take a very quick commercial break. And when we come back, I'll be speaking to Dr. Matt Taylor, the project scientist on the Rosetta mission, about the spacecraft and what it's done. Well, welcome back to our live coverage here of Rosetta and Comet 67P Churyumov-Gerasimenko at perihelion. In a couple of days, the comet is going to reach its closest point to the sun, a moment that astronomers call perihelion. And it's really an opportunity to study how comets evolve as they come through the solar system. And someone who knows more about comets than many people is the project scientist on the Rosetta mission, and that's Dr. Matt Taylor. I'm incredibly lucky to be able to speak to him live right now. Dr. Taylor, thank you so much for joining us here on SLU. We're so lucky we managed to get live pictures of the comet. And I guess one of the things that, for me, I think is so special is that your team and Rosetta has actually provided us an incredible close-up view. And so this dot really becomes almost a world in itself.
Yeah, I have to highlight, it's really important that we have these ground-based observations, both from the professional side and the amateur side, because that just gives us a fantastic context. If you consider, I think, all the images that you can see, that we're in that dot, that nucleus is in 1 pixel with this spacecraft around it. So we haven't got that context when we're right up close. So it's highly important.
I think the last time I spoke to you, it was June of last year, and it was wonderful because when I was talking to you, you had so many questions, and I kind of feel over the last year, some of those questions we've started to know a lot more about. I mean, when I spoke to you last, we didn't even know what this comet looked like. It was just a dot as we were approaching it. How have things changed for you in terms of, you and your colleagues' opinion of this comet? What have you basically learned in the last year?
I think we knew this in the beginning, which was to expect the unexpected, and I think that's what we've learned, to even more expect the unexpected. I think, yeah, you highlight one of the most striking things that immediately came across from this comet was it changed from this grey potato, which I have a model of here. This is the, excuse me, sorry for running away. This is the old model that we had of the comet. Based on Hubble images. So it's this grey potato. And then it obviously changed into the duck-shaped like body that we know now. For me, that's one of the most striking things that happened to us here. But in terms of what we've learned, I was asked this the other day, and I'm reticent to say we've learned this, that, and the other, because I look at Rosetta as up until the end of the mission. It's really, I wait for the end of the mission, and then we look back and look at the data as a whole because the whole point, and I think you mentioned this earlier, is for us to understand how the comet works. So I think we'll really only get that once we've seen the full activity cycle, and that's the key thing here.
Well, perhaps then that's a great opportunity to sort of go back to the very beginning. Where did the idea come to visit a comet like 67P?
Well, I think the idea was born in the days of Giotto and Halley's flyby. Rosetta was actually originally a comet sample return mission in combination with NASA. Actually, I could swing. I'll be back in a second. I'm just thinking an audio or visual guide might be helpful. This is a document. This is a report of the joint ESA NASA team. You probably can't see it here, but this is from about 1987. So this was a report that was looking at what you'd want to do to go and grab a piece of a comet and bring it back to Earth. And quite soon after that, it was deemed that was quite an extravagant thing to do. So the next best thing to do would be to send a probe and deliver something onto the surface and do an in situ study. So this was in the 80s, as I say. So it's taken that long to develop and also to get there as well.
Yeah, it's something like 10 years, isn't it? And why did it take so long?
The main problem is trying to get enough stuff off of the Earth, and these things, well, for our comet, which we see here, which orbits out to Jupiter's orbit, you just haven't got enough fuel to get there. The orbital dynamics that require you to rendezvous, which is one of the key things that we have with Rosetta, is that we actually entered the same orbit around the sun that the comet had. So rather than just you can't just bolt straight to it. You have to do a bunch of flybys. You just can't take up enough fuel, basically. So you have to borrow some energy from various planets with their gravity, doing these little slingshot maneuvers that we're all familiar with when we watch Star Trek. That you do that, and then you get the orbit kicked out. So we're able to rendezvous with the comet successfully just over a year ago now.
Yeah, it's just over a year, a few days, isn't it? And one of the things that you mentioned back when I last spoke to you is how difficult it is actually to fly around a comet. Has your experience over the last few months really sort of borne that out? Has it been a real challenge to sort of stay in orbit around the comet?
Yeah, even more so. Actually, we had concerns that we would not make enough dust measurements a couple of months ago, but late last year, and when we were planning for the observations we make now. And it is completely the opposite case. In particular, we need, through navigation, we need to be able to see the stars. We have these cameras, special cameras or detectors that are called star trackers, and they are getting very confused by that material that you see there flying out off the comet nucleus. So the dust in the coma confuses the spacecraft significantly, and we can't have that because that jeopardizes the mission itself. If we lose the spacecraft, that's something we don't want to do. We basically need those star trackers to be locking onto stars so we have accurate pointing information. If we lose accurate pointing information, even basically the steerable antenna will start drifting away from Earth. We're pointing to Earth so we know where we are, and we'll lose the spacecraft. So that's been one of the major challenges that we've had to face, is the fact that the star trackers are seeing, or the dust environment is different to that we expected. So that's meant we have to fly further away from the comet, and that's where we are at the moment. In fact, in the last week or so, I think at the beginning of August, we were around about 180 kilometers from the comet, but we very soon had to run away, as it were, because we were having trouble again trying to keep lock on the star. So now we're about 300 kilometers, and that's indicative. If you correlate the activity of the coma with the star trackers, it's showing that the comet is becoming more and more active, and you can see this from the images that you're showing here. In fact, this is from about 180 kilometers, but now we're at about 300 now.
It's been absolutely beautiful to see how these beautiful jets have sort of developed over the recent months, and I know we're going to be talking a lot more about that after the break. But I wanted to talk briefly about Philae, of course, because that, in a very sort of real sense, is one of the real challenges of the mission. When you were designing the mission, when you were sort of coming up with it, was there any sense that this might not work? I mean, we know now, sort of with the hindsight, there was an incredible landing or multiple landings. But did you or your team members have any doubts?
Well, in hindsight, I can say we didn't. But you know, the mission was designed with quite large margins. I think if we look back at some of the older missions that have been to comets, you know, such as Deep Impact, etc., we were using information. Well, that was actually after launch. But when we launched, we had a perception of what the comet's surface would be like, but it was quite a broad range of material that we were thinking it would be like. So one of the worries actually was whether the tensile strength and compressive strength of the surface would be enough to support the lander. But I think there was a discussion at one point about whether, or when we were trying to find a landing site, is trying to avoid some of the more dusty areas that we see. So some regions just look like they're absolutely billowed and covered with a, you know, like a new drift of snow, but it's dust. But when the lander would hit, it might just sink down. And if it sinks down, you'd lose all the solar panels, and then we wouldn't have a mission at all. So there was a lot to consider there, but there were very broad range parameters. Actually, something to I should come back to the beginning with the mission. We didn't originally plan to go to this particular comet. The plan in 2003, I think, was the original launch date, was to go to Comet Vatanen, which is a much smaller comet. I think it's about 1 kilometer across nucleus size. So it was a different environment, and we couldn't change much on the spacecraft and the lander for that change. So we were on the edge anyway in terms of gravity, etc., for this bigger comet that we've landed on.
It's been an incredible mission so far, and I wanted to talk very briefly just about sort of the science instruments that you took with you, because we not only just getting amazing pictures that you can see on your screen, but you've also been collecting just absolutely enormous amounts of other data, haven't you, from the different instruments?
Yeah, it's really important to realise that we have a massive suite of instruments on board. Again, I alluded to the fact that the original mission was a comet sample return. So that's where you get your stuff and you bring it back to Earth, the laboratories on Earth. We did the next best thing. We took as much of a laboratory that we could up to the comet itself. So we have remote sensing of different wavelengths, as you can see here. Most of I think about 80 or 90% of the instruments are all on one side of the spacecraft as well, which is another thing that causes particular operational challenges when you're trying to have one instrument that wants to look at the comet and another instrument that wants to look at 90 degrees to the comet. And these are some of the wonderful discussions that I have to get involved in and try and mediate. But we have, so remote sensing, infrared, UV, and also visible spectra, as well as things that sniff and taste the comet. So gas detectors, dust detectors, there are several dust detectors, as well as my background, the plasma instrumentation. And that's actually something that has been very interesting, seeing how the plasma interaction is working around the comet. And again, all of this is important, that it's not just a snapshot. We're seeing the evolution of all of these measurements over time. And when we go to Philae, there are specific instruments on there that are designed for if you want to scratch and sniff the surface of the comet, which we just about did, quite significantly, in fact. So there we have, again, things that sniff and taste the environment around the comet. There we can see actually the deployment there of one of the hammer on the Philae lander. And most recently, we've had the first results that we had during the first science sequence of the lander come out. And we see really what the comet surface is like, that it actually has a very, very hard subsurface. And again, going back to our considerations of what could be there and couldn't be there, we were worrying about the fact that the lander might actually sink through the surface of the comet, that the comet surface, its tensile strength wouldn't be big enough to be able to cope with something landing on it. And we found that, in fact, it was strong enough to allow this 100 kilos of lander to bounce across the surface of it.
It's so surprising. We're going to talk lots more about some of the science results, both from Philae and Rosetta, after the commercial break. But we're going to have a very quick break for 30 seconds. But remember that there's lots going on with SLU this week. As I said earlier in the show, we have our Perseid Meteor Shower live show coming up. And we've got a fantastic range of stuff from radio meteor detection and also some live cameras spread through all our global partners around the world. And that is on Wednesday, August the 12th at 8 p.m. Eastern Time. And then we are going to have a show celebrating Comet 67P at perihelion. That's also on Wednesday as it reaches that actual point that's the closest point in the comet's orbit to the sun. So lots to look out for on SLU. We're going to go to a very quick commercial break, but afterwards I'm going to be talking to Dr. Taylor about some of the science that the mission has returned. Well, welcome back to our live coverage here on Slew.com of the Rosetta mission's approach to perihelion. That approach as it orbits around Comet 67P, as the comet comes into the inner solar system, it's reaching its closest point to the sun. And we're actually bringing you live images here on your screen from our telescopes in the Canary Islands. That beautiful cluster of stars is Messier 35, and the comet is just down there in the bottom left-hand of the corner. And it's fantastic we've been able to get these pictures because we've been sort of battling cloud up on the observatory there. But we're actually very lucky to be joined by Rosetta's project scientist, Dr. Matt Taylor. And before the break, we were talking about the spacecraft itself. But I wanted to talk a little bit about why comets are interesting objects to study, Dr. Taylor. I mean, what can we learn from them?
Comets, along with other small bodies of the solar system, are considered to be like the leftovers, the debris that was deposited after the formation of the solar system. And comets, I have to say, are particularly interesting because they were slung out into the outskirts of the solar system. So the material that they contain within the comet, we find material that is very pristine. It's stuff that was there at the beginning. So by studying these bodies, by looking at comets, we get an idea of the material that was in existence in that state way back, 4.6 billion years ago. So I think that's the biggest hook you can have for comets, in particular from a human perspective, is where do we come from? They really are tapping in to that specific question. How was the solar system formed? What was the material that made up the solar system? And in particular, connecting to us specifically on the Earth, why are we here? What makes us so special on the Earth? So far, we haven't found other living organisms in the solar system apart from on this planet. So what makes us special? So it's that big picture story that we address by studying comets.
I think one of the most amazing things from this mission has been those early images that really sort of showed this incredible craggy sort of angular sort of shaped comet with these incredible lobes. I mean, I made a model just not long before Rosetta arrived at the comet to try and sort of put it together. I mean, I just couldn't even sort of imagine that it would sort of look like this bizarre object. Is this the sort of thing we expect a comet to look like? I mean, how has Rosetta sort of changed our sort of view of comets, if it has? I mean,
well, if you look at other comets that we've visited, we have seen this bilobal-like structure. I mean, I think you might even be able to argue that Halley had a little bit of a bilobal structure, but it's not something as uncommon, as it were. But I think the thing that is very striking is how, as you say, craggy and angular and undulating the terrain is on the comet. When we first saw the comet, a lot of people were indicating various regions and comparing them to other comets that we've been to, Hartley and Wild. And it's apparent that, or at least for me, that it was a good, in hindsight, it was a good comet to go to because it displays features that all of the other comets that we've passed by have. So it kind of combines all of the features that we've seen before on comets, which I think is good. Again, going back to the ground-based observation. So if you consider this is a bit like a calibration. So if we have an in situ measurement with Rosetta, so Rosetta's there on this particular comet, and we have all of the scopes on the ground and also the near-Earth observatories looking at the comet at one time or another. They're not looking at it all the time. You can kind of calibrate those ground-based observations, and so what we learn from doing that matching, we can then apply to all the other comets. So I think that's at a global level a really important thing to take on board, and that's why it's very important for the community on the ground, in particular the amateurs, because they're able to unleash their own wants. Yeah, they don't have to write proposals. Lucky them. And so we get much longer baseline observations from the ground-based amateur community, and it's fantastic. It's actually been very useful because some of the larger professional telescopes we couldn't use to see the comet in recent months. It's only now it's starting to come into above the horizon, as it were, for some of the bigger scopes. So all of this is very important in the global sense for scientific endeavour, to get an idea of how this comet evolves, and then also to apply that to all the other cometary observations we have.
And I guess we kind of mentioned it earlier, that one of the things that links into this sort of professional amateur collaboration is how watching that comet evolve from that sort of dot and how it grew the coma, and also your observations showing those beautiful jets emerge. I guess it's important to sort of see that evolution, right?
Yeah, exactly. It's fundamental. As I say, the mission's there because it's escorting the comet at about 1 meter a second. So it's actually right next to the comet. It's there to see this evolution, to see how this activity grows. Likely will peak just after perihelion, based on some of the observations we had from the last apparition, and then wane away and then die off. So that's the key thing. And again, having those context measurements from the ground are really important. In particular now, when again going back to the unexpected, just in case something goes off, when we do see these large emissions, these large jets, we had something recently that was quite striking. It doesn't appear that it came up on the ground, that we could see it from the ground, but more of those are going to occur. We see them in the images. I think you were showing them before as well, as some of the NavCam images, that something striking might happen that we'll be able to see from the ground. The last apparition showed significant structure post-perihelion that we're able to detect on the ground. Now, being able to see that, so these very large jet structures were studied. If we can see those when we've got Rosetta there and from the ground, that's going to be fantastic to really get an idea, again, for that connection of global cometary dynamics that you can connect to everything else, but specifically for this fantastic comet as well.
We've actually got a question from someone watching on Twitter. Chrissy asked, where is 67P in relation to the sun from the viewpoint of Earth?
Right, I'm going to have to think about this one. It's difficult to... You know what? I did have a diagram up earlier on. I might have to just draw it. It's...
I guess,
hang on a second.
If Chrissy's thinking in terms of constellations, I mean, because we have M35 there, it's going to be in the constellation of Gemini. So if you know where Gemini is, Chrissy, the two bright stars, Castor and Pollux in Gemini, it's going to be at the foot of the Twins. Gemini is the Twins constellation. But I think it's, from what I read earlier, it's about 266 million kilometers away from Earth. Does that sound about right to you?
Yeah, it's something about that. But I mean, in terms of location, here we go. You've got the sun there in the middle of the solar system. The Earth is kind of here, and then 67P is going through its perihelion here. So about 1.2 AU. So we're kind of just about skirting and following it round the sun. But as I say, about a few million kilometers away from it, a few hundred million kilometers away from it. I think actually it's about 200, so we're 180 million kilometers from the sun during perihelion. So the Earth distance is around 270,000 kilometers. Yeah, as you say.
Yeah, so it's an incredible distance. Going back to the pictures and the sort of the changes that Rosetta has seen at the comet, one of the things I was fascinated about is those recent OSIRIS images of the ice sort of exposed on the surface, and also those sinkholes with the apparent jets coming out of them. What do we think is going on there?
Well, one of the big questions we have is how activity works. How do we drive the coma? Where does the coma, the outer atmosphere of the comet, come from? When we were approaching last year, we could see a specific amount of material being pushed off the comet. So we are talking something like 300 milliliters of water, of H2O per second coming off. And that emission you could correlate at the time with something like 99% of the comet not having any surface ice. And it kind of fitted with the kind of observations that we were seeing. But maybe one would say that there doesn't appear to be enough ice on the surface to drive the activity that we're seeing. But I think it's because the situation is much more complicated than that. As you're alluding to, okay, we've actually seen surface ice, but it seems to be in shaded regions. So where is the ice in the illuminated regions? It could be that subsurface material is where we're getting this emission from, where the sublimation is actually occurring from. And this is stuff that we thought of and that came out of previous missions, again, like Deep Impact. That's
so this is
where we are, and then we can add on to this. Yeah, sorry, I was just trying to remember that to link into J.B. Vincent's paper on the sinkholes. That's that's the big one. Is now we can actually see surface features and correlate them with activity, and that's another thing that we'll be doing in this time frame, because the activity is highest, is to then pinpoint on the surface where we think things are coming from, and then after perihelion go down and we'll be able to see what the changes were on the surface layer to do, another analysis of before and after, before something kicks off in a major way. We can go back and look on the surface features and various wavelengths to see what might have driven that. And the sinkholes appear to be a nice idea in terms of what and how we're getting material from the comet. That not is just, the comet's not a big bright shiny ice surface. It's very, very dark and covered in a lot of dust. So how is the stuff that we're seeing? And there's a lot of it. We're talking hundreds of kilograms per second of water alone coming off of the comet at the moment. So it's coming from somewhere, and it's, the sinkholes and also maybe subsurface sublimation that's linking directly to the surface. And this is ongoing at the moment to try and find out what that is.
And I guess that's why this moment of perihelion that we're approaching in a few days, that's why this is so exciting, because it's coming up to a maximum. We expect this activity to be at its peak.
Yeah, I mean, I've spoken to a couple of people, and maybe some people have got the New Horizons picture in their head that, it's like bang, and then that's, like perihelion's going to be this massive increase. It is the period now. So the beautiful images you were showing before from both the ground and at Rosetta, it's getting active now. It's been active for since last year, actually. It depends on what your level of activity interest is. But that occurs around the period of perihelion, and within the month afterwards, so into September, that's where we see the peak. One thing that's really important to highlight here, and I'm probably better to show from your big comet model, is that last year when we first started making this comet, this comet 3D structure and getting a feel for it, there was a large part of the comet we couldn't see that was not in sunlight. And you see that from your model. There's a bit that doesn't look really well resolved. There's about 30% of it at the beginning because it was not sunlit. It was the southern hemisphere of the comet. If you consider the comet to be a duck, if you think a duck has fallen over on its right wing and then is rotating beak first, that's how the comet rotates. Now, that right wing was not illuminated by the sun up until around May this year. Now, there you go. There's the duck rotating on its right wing. We are now moving. We've gone through equinox, so we're in the southern hemisphere summer now, from May this year through to March next year. It's a very short-lived period of time that the southern hemisphere gets illuminated. So that's an important thing to consider. The comet's orbit around the sun takes about 6.5 years, but only over that short time period of less than a year, about 11 months, that part of the comet actually gets illuminated. So that's even more pristine. There's even more material. Likely, if we just consider the whole solar energy into the comet, this input to drive sublimation, that's very short-lived for that region. So we should see, and we're beginning to get inferences, and hopefully we'll start to get a little bit more of that information. And maybe as a little teaser, you might get a little bit of a show of that during the perihelion show that we have to see what that region looks like. And that's the thing that excites me. And we, as I say, we're starting to see more activity. Is it being driven from that region alone?
Fantastic. Well, thank you, Dr. Taylor, for coming on to speak to us here on SLU. We hope you'll come back maybe in a few weeks or months' time and sort of tell us what you've found.
It will be my pleasure, as long as I've got some coffee, because it was a bit of an early one this morning.
Absolutely. So thanks for getting up early on your morning, and we're going to be following 67P for the next several months, studying it with our telescopes here at SLU.com. And I'm going to be speaking to Paul Cox, our observatory manager, later on in the show about exactly how we're doing that and how you can get involved too. But there's lots more coming up on SLU over the next week. We're watching 67P at perihelion. We'll have a live show on Wednesday, the 12th of August at 1 a.m. Eastern Time. And then, of course, we have the Perseids meteor shower, that fantastic summer meteor shower. Get all your friends together. We've got a fantastic show lined up for you. And that's also on Wednesday, the 12th of August at 8 p.m. Eastern Time. But for the moment, we're going to have a quick 30-second commercial break. And when we come back, I'll be speaking to the telescope operator and astronomer at the optical ground station there on Mount Teide at the observatory about what we're looking at tonight and what we're trying to get pictures of. So see you in about 30 seconds. Well, hello and welcome back to our live coverage here on Slooh.com of Rosetta and Comet 67P's approach to perihelion, that moment when the comet is at its closest point in its orbit to the Sun. And tonight here on Slooh, we've been trying to bring you some live pictures of the comet. It's a real challenge because not only is the comet quite faint, but also there's been a little bit of cloud bubbling up around the Canary Islands, around our observatories. Now, our observatories are located in one of the best sites in the world to do astronomy, fantastically clear skies, and there are lots of observatories in Tenerife and even next door La Palma to study the night sky and study the universe. But unfortunately, we've been up against a lot of cloud, and actually, there you can see it in the all sky image. It's sort of bubbling up over in the eastern sky there and causing trouble. And we've been racing against twilight to try and bring you those pictures. But I want to bring in now one of our partners who's at the optical ground station there in live from Tenerife, and that is Yuri Casella, who's the operator and astronomer of the telescope. Yuri, thank you so much for coming on this morning. It's been a real sort of exciting race to get those pictures. Has it? Obviously, we haven't got the pictures from the optical ground station so far. What sort of challenges have you been facing with the telescope tonight?
So basically what we have is there's some clouds, but that's not the biggest issue because some of them there were some holes. But the problem is that we have a high humidity. We have 100% humidity. So basically we should not even open. But we wanted to try, so we opened.
Well,
and we found out that there's a huge condensation of water in the front window of the camera.
We're hugely grateful for you trying it.
Yeah. So basically, we got it more or less in a condition, but now the sun is coming up and the sky is coming bright. We will not see anything anymore.
Yeah, it's one of the challenges of ground-based astronomy. Unfortunately, like Rosetta has the challenge of flying around the comet, we have to sort of deal with water vapor and other stuff in between, isn't it? But tell us a little bit about the optical ground station itself. I mean, what's your work there involve?
Yeah, so the optical ground station was set up to do a laser communication experiments. And one of the first satellite was Artemis satellite. And it had the payload to test laser communication. And when we started this telescope, at the same time, it was decided that we also want to use it for space debris observations because it has quite large field of view. And nowadays also we observe near-Earth objects. So I'm mostly involved with the space debris and these near-Earth object observations. And the issue with the space debris, of course, is the speed. You see these astronauts flying nicely around the space, but actually the speed is really huge. For example, International Space Station is 7 kilometers per second. It's difficult to understand what it means, so I often tell the people that, okay, let's think about it. You take a pistol and you shoot. The bullet which comes out flies around 400, maybe 600 meters per second. And now these pieces there in space, they fly 10 times faster. So if you hit with them, you really get a big problem. So how it looks like is something like this. This is an experiment done in the ground. This is a solid block of aluminum. And the ball which hit the aluminum is the size of this.
That's extraordinary. Well, we're immensely grateful for you trying to image the comet this evening, and hopefully we'll come back to you in a few weeks' time and speak to you and see if we can have another go at looking at 67P. But thank you very much for coming on to Slooh this evening or this morning there in the Canary Islands, and we're actually going to have a short commercial break once again, and we're back in just 30 seconds when we'll be talking to Paul Cox, Slooh's observatory manager, about how Slooh and Slooh's telescopes and even Slooh's members have contributed to the understanding and the study of Comet 67P, the comet that Rosetta is visiting. So join us in 30 seconds and we'll be talking to Paul Cox. See you then. Well, hello and welcome back to Slew's coverage here of the Rosetta Comet 67P Churyumov-Gerasimenko's approach to perihelion, the moment when it reaches its closest point in its orbit to the Sun. And we've been bringing and trying to get live images of the comet. Earlier in the show, we spoke to Dr. Matt Taylor, who's the project scientist on the mission, and he talked a lot about how ground-based observations are very important to studying the Rosetta's Comet 67P in order to sort of get a ground truth, to sort of understand it. And that's something that we've been doing here at SLU. And I want to bring in now our observatory manager, Paul Cox, who's been very involved in the project to sort of coordinate these observations and also help the SLU members as they're observing the comet and other comets and asteroids. Paul, it's quite an expansive project that SLU has in the clubhouse, isn't it?
It is. It's absolutely huge. I just want to remind people that I'm not actually Dr. Matt Taylor in another guise. I am Paul Cox. So we'll just change that little label there. But yes, and wasn't it fantastic to hear Matt, a professional astrophysicist, talking about the contribution that amateur astronomers can make. And the project that SLU members are working on at the moment is it's called a Pro-Am collaboration, and it came out of Comet ISON, that comet that was meant to be Comet of the Century and all of that, but it kind of went out with a bit of a fizzle. But the project that came up for that, the Comet ISON Observing Campaign, set the precedent for what we're doing with 67P. So we're working very, very closely with ESA scientists and other astronomers, and we're contributing our image data. So SLU members every night are setting up the telescopes, controlling the telescopes we use tonight to image 67P. That's what we're looking at now. This is a SLU member's image of Comet 67P. And this gets submitted to this collaborative group and shared with the professionals. And one of the great things, Will, is if a member's image is used in any paper, scientific paper that's written, their name actually gets added to the paper because they've contributed their data and their work to that scientific paper. So it's really exciting stuff that people can do.
What sort of measurements can these images allow us to make about the comets or the asteroids that are in them?
Well, there's two kinds of measurements, really. One is positional. So in other words, where is it? What's its orbit? Those positions are used to calculate the positions. And in fact, SLU members, we have a whole training program where members from scratch, virtually scratch, you don't have to have very much knowledge at all. We actually train members how to monitor and track both near-Earth asteroids and comets. So they take an image of the comet and you basically measure its position in relationship to the surrounding stars, Will. And we then submit that to the Minor Planet Center. But we can also, from 67P, it's a periodic comet. That's why it's got the P in the name. So it comes around every once in a while. So we know its orbit really with quite a high degree of accuracy. But what we don't know is its brightness, because that changes on every visit to the sun. So how much it's outgassing. And we measure its brightness, and we also submit that data. And that's what Matt was talking about. Dr. Matt Taylor was talking about this calibration. For the very first time, we're looking at this image. So this is taken by a SLU member of Comet 67P. We can measure its brightness in relation to the background stars. But Rosetta was there at the time this image was taken. So they could close up monitor the actual activity, how much outgassing, what kind of jets were coming out of the comet, so that we can calibrate what we see in these ground-based images from SLU members and the professional observatories and what Rosetta's seeing. And we're going to be able to roll that calibration kind of information back, Will, through all past observations of comets as well. So this mission really is going to open up cometary science a huge amount.
It's really exciting. And of course, one of the things I think Matt actually alluded to, and it's cool about our telescopes, is we can not only do this for much longer than the professional telescopes, but we can also see the comet when it's much lower down as well, isn't it?
Absolutely. And in fact, SLU members were one of the first people to around the world to be able to image 67P when it came back from when it got hidden behind the sun. And this was possible because of SLU's Southern Hemisphere Chile Observatory, and we got some of the earliest images. And you see, professional telescopes, often they can't look very low down on the horizon. And most comets actually hover kind of most of the time, either at dusk or at pre-dawn. And SLU's telescopes can go really, really low. But what we saw tonight, Will, is we were able to open, even though the weather conditions were against us, but the big OGS telescope, which the ESA guys did such a wonderful job for us tonight. This is part of our Megascope series where we're doing these shows. We had the EACS Carlos Sanchez telescope where we did that live exoplanet transit, if you remember. Those guys tried so hard tonight, but they couldn't. They had too much moisture where their observatory is. There's about probably about 500 meters between their observatory and ours, but the microclimate up there can do all sorts of things.
Well, I know we're going to be coming back to 67P, and we're going to be doing actually lots more live shows of comets and asteroids over the coming weeks. So I'm sure we'll hear lots more about what we're doing in the clubhouse. But of course, we have got a fantastic week coming up, really, of shows, haven't we?
Because we have.
You're going to be organising. You've got quite a show planned for the Perseid meteor shower. You've got your meteor shower checklist there on screen, and it's going to be a fantastic shower, the Perseids, this year, isn't it?
It is. We've got no moonlight to spoil the view. This is probably my favorite meteor shower, Will. And of course, a meteor shower is linked to comets because the meteors are caused by all the dust and debris that's left off by the comets. But we're going to explain all of that. You and the other SLU astronomer, Bob Berman, you're going to do the scientific bits in bite-sized chunks for the whole night when we watch the Perseid meteor showers. And I'm going to be doing loads of live segments reporting from outside the SLU studio in Connecticut. We're going to be watching the stars just like everybody else. So what we want everybody to do, Will, is join us back here at SLU.com on Wednesday night, 8 p.m. Eastern time, with these things: a lawn chair, hot drinks, laptop or cell phone so you can listen to us, bug spray, really important, picnic, and some warm clothes. It doesn't matter if you're clouded out because we have got live views from all around the globe. So we're going to be able to see the Perseids on screen. We're going to be able to listen to them as well. Let me just clarify one thing, Will, as well, from earlier on. Our 67P show, the perihelion show, this is when it's closest to the sun. That's on Tuesday night. It was labeled up as Wednesday, but that's actually Tuesday night because it just goes after midnight. And it's the Perseid meteor shower on Wednesday that we want everybody to come and join us. That is going to be, I think this is going to be one of the best nights we've ever had on SLU. We are so looking forward to it.
Yeah, I'm really looking forward to it. Paul, thank you for coming on. It's always wonderful to speak to you. So enthusiastic, and it's great to hear all the amazing things that we're doing in the clubhouse to follow these comets. For us, that's really coming to the end of the show. I just want to thank everyone at the IAC over in the Canary Islands for that tremendous effort of getting the optical guides scope sort of pointing in the direction of the comet. Thank you to Dr. Matt Taylor, project scientist on the Rosetta mission, for coming on and giving us his perspective and talking about that incredible science that mission is doing. And thanks also to Yuri Casella, who's the director of Ataman Science, who was the OGS operator and astronomer there we spoke to just a few minutes ago. But from me here, I hope you've enjoyed the show, and I hope you'll investigate some of the things we're doing here on SLU. We'll see you again next time on SLU.com. But for now, good night.